right, so this is heat transfer vocabulary, or notes on heat transfer. And this, remember, these are the notes with additional challenge added in. So if you are looking for more than the average level of challenge, these notes are for you. So I would assume in these notes you already understand when I say phases of matter and phase change, all that vocabulary that goes along with it. And I'll be using that vocabulary within these notes. So if you realize there's something you do need to go back and look up, you can do that. But if you feel like right now this would be too much, go back and do the other ones. You don't need to do both. All right, so let's first talk about heat and temperature. So heat is energy transferring between two types of matter. So when we're talking about heat, we're talking about energy. And so if you remember matter, matter is anything that has mass and has volume, or takes up space, and is made of particles. Energy doesn't have any of those. It doesn't have mass, it doesn't take up space, it's not made of particles, but it's still very important in our world, right? Light, for example, is energy. If there were no light, we wouldn't be able to see. And energy is always measured in a unit called joules. And we abbreviate it with a J. And sometimes we see it as kilojoules. If like kind of kilometers, kilojoules, it would be 1,000 joules. Temperature then is the average amount of energy in the particles of a type of matter. So it helps us understand how hot or cold something is based on how much energy the particles in the matter have. So it's not energy transferring or moving, it's the average energy of the particles. And that's measured in degrees, like degrees Celsius or degrees Fahrenheit. So then heat always moves from hot to cold, or from high temperature to low temperature. So the energy is what's moving. Okay, even though it doesn't have mass or take up space, it can absolutely move. If you think about, you know, gathering around a nice warm campfire, right, the energy is going from the burning wood really into you. Well, into the air and then into you. So here we have a stove, and you just have to take my word that it was a hot oven. And so if it's hotter in the oven than in the surrounding air, the energy moves out. Now, it's possible that some air moves in, but air is matter. And we're not talking about matter right now, we're talking about energy. So the energy moves out, which is why if you're baking something and you open your oven for too long, when you close it again, you've lost so much energy, so much heat, that the oven has to work harder to heat back up again. And I know there's some statistic like every time you open it, it drops 50 degrees or something like that. But obviously the longer you keep it open, the cooler it's going to end up, the more energy you're going to lose. On the flip side, if you have a freezer, okay, same room temperature air, but now it's a higher temperature outside than inside, so here the energy is going to move in, and that's going to heat up. The more energy that moves in, the greater the temperature you will have, because it's going to increase the energy of all the particles in the freezer. And then it's not going to keep your food frozen. So that's why you actually have a motor on your refrigerator that will remove energy when the temperature gets too high, either in your freezer or your refrigerator. All right, so now let's look at how this works with solids, liquids, and gases. And as I said, I assume you already have your phase change vocabulary: melt, boil, evaporate. You know the difference between evaporate and boil. You know what sublime is. You know what freezes. You know what condenses. If any of those are new, you may want to look them up on your own time. And then here we have three representative states of matter with the same matter. So we have ice or solid water, we have liquid water, and then we have what we would call water vapor or gaseous water, or sometimes we even say steam, although technically that's not gaseous water. And you can kind of see some bubbles going on in here. It's not a great picture, but it'll do. So when we move from solid to liquid to gas, we are adding energy. So you can tell, like right here, right, the stove is on to get this to go from liquid to gaseous water. And by the way, that means that inside the bubbles, that's not air, that's actually water vapor. And because it's the water that's now becoming gas. And when we add energy, anytime we add energy, we call that an endothermic reaction. N, the root N meaning enter. And that's why the word enter is what it is. So energy is going into the substance. On the flip side, we are removing energy when we go from gas to liquid to solid, and we call those exothermic. The X from like exit, and again, that's why that word is what it is. So the energy is exiting the substance. And so this brings up an interesting question of like, if we're adding energy, where does it come from? And if we're removing energy, where does it go? So it's pretty obvious to see here, right? We're adding energy and it comes from the stove. But what about the ice cube melting? If I just leave it out on this counter for long enough, the ice cube's going to melt. Where does that energy come from? So pause the video, kind of come up with an idea, and then start the video again. So the energy comes from the air. As we just talked about, heat, which is energy, moves from warmer substances to colder substances. So the surrounding air is warmer than the ice, so the heat moves to the ice cube, which heats up the ice cube to a point where it then can melt into liquid water. So then now let's talk about exothermic. What if we are freezing the water into ice? Where does that energy go if we have to remove it? Again, pause the video and see what you think. So it actually goes the same place. It goes into the air, which is why if you put like a bunch of liquid water in ice cube trays into your freezer, well, now that water is going to be warmer than the surrounding air in the freezer, so the heat is going to move from the water into the freezer. Now, eventually, if you didn't have a motor on your freezer, the freezer would just heat up, or it would warm up. I mean, it wouldn't get hot, but it would get warmer. Because you have a motor on your freezer, when too much heat has gone into the surrounding air, the motor kicks on and it removes a lot of that heat, which is also why if you've ever felt like, some people have actually felt the back of a refrigerator. I don't know why you would, but I've always had some students who have. You notice it's really hot because it's pulling that energy out. All right, so let's now talk about surroundings versus substance. So without looking back at your notes, see if you can remember which of these changes, water to ice or water to vapor, is endothermic and which is exothermic. All right, so hopefully you said water to ice is exothermic, so heat is being removed. I'm going to put an R here. And hopefully you said water to vapor is endothermic, so heat is being added. It's entering. Okay? So entering, exiting. And now if we talk though about what's entering or what it is entering or exiting, so here we're saying heat is exiting the water, so the substance loses energy, but then the surroundings actually gain that energy. So when we're saying exiting from the substance. Okay? On the flip side, here, when we're saying heat is entering, it's entering the substance. So the substance gains heat, but it's actually exiting the surroundings. So the surroundings lose heat. So just understand when we're talking about exothermic or endothermic, we're talking about exiting or entering the substance. Now, so far we've only talked about phase changes, but this also works for chemical reactions. And chemical reactions are when you get a completely different substance from what you started with. So here, this started as liquid water and it ended as frozen water. Here, this started as liquid water and it ended as gaseous water. But, for example, when we did the station rotation at the beginning of the matter unit, we put Alka-Seltzer, those little white tablets, into water. And then we noticed that the temperature of the water decreased. So was that reaction endothermic or exothermic? So go ahead and pause the video and see if you can figure that out. So hopefully you said it was endothermic, although I'm sure a lot of you actually said exothermic. You were thinking exothermic because you were thinking, well, the ice got colder, and so the stuff in the test tube got colder, and so it must be exothermic. But in fact, it's endothermic. And the reason is, this means that, and this gets into what chemical reactions are, in order to break apart all those atoms, you needed to take a bunch of energy from the surroundings to get that reaction to happen. And so what you were actually measuring the temperature of in that case was the surroundings. And so the surroundings lost heat, and then the actual substance, which in this case we're talking about bonds between atoms, those gained energy, and it was used to break everything apart. This is a really, really sophisticated concept that you will come up against again in biology in 10th grade and then in chemistry in 11th grade. So, trying to capture it all in 7th grade is really hard. It's easier in 7th grade to stick with phase change. One thing I do want to say is going back to where the energy goes, and it goes into the surroundings. So that's why like a steam burn hurts so much, because when the steam hits you, it condenses into water, and all that extra energy that was keeping it gas goes into your hand. And so a steam burn actually hurts more than a boiling water burn if it's liquid water. And it's just kind of an interesting concept, because it's giving up all that energy that was keeping it gas, and now it's liquid, and that energy has to go somewhere, so it goes into your hand. All right, so please feel free to ask questions if these concepts are confusing. If the endothermic, exothermic on the chemical reaction here is a little too much for you, that's okay. This is a concept that my biology students who are taking 10th grade biology are going to struggle a lot with too. So don't sweat it on that one, but make sure you understand it on the phase change. Have a good day.